This is chapter 13, lesson 4. So this is application, really, of the previous lesson, lesson 3. All right, and we're going to start. We're not going to do the computer simulation part of it. Although, if you work in statistics, actually, if you probably work in any industry, computer does most of the calculations for you. Except I do know my son actually has to come up with the formulas, but I don't think you have to in statistics. Somebody has to design it, but probably you're just going to plug in numbers and poof, the numbers come out, right? Okay. So we've already talked about the probability of an event happening, right? This is rolling a number cube. There's one number cube, right? Are any of the outcomes the same? No. So the event is mutually exclusive, right? If I were rolling two number cubes, then the events can overlay, right? So I am multiplying. That would be an independent event. Okay. So example 3 is a mutually exclusive event. Write the probability distribution. Look, they have. Every option, 1 through 6, is 1 out of 6, right? Then it says, find the probability of the event that an even number is rolled. Well, what are we doing? We're adding 1 6 plus 1 6 plus 1 6, which is 3 6 or 1/2, right? Because it is a mutually exclusive event. Got it? Okay. Now, look at example 4. So that was a mutually exclusive event. This one is going to be an independent event. It says, use properties. Wait, okay, so we have to go back to example 2. What happens? We're tossing 3 coins. All right, we're tossing 3 coins. All right, so we have to write the probability that there are no heads. So 0 heads, this is the number of heads. And this is example 5, but it goes 4, but it goes back to example 2. So we're tossing 3 coins, all right? And this is the probability of that many heads. Okay, 0, 1, 2, 3 are the most that we could toss. Okay. No heads means what did we get every time? All 3 tosses? Tails. So what's the probability of one time I get tails?
You take 0.5 times 3.
I'm multiplying. That's event 1. That's event 2. That's event 3.
Which is 0.125.
0.125. So the same would be of 3 heads, because this probability of getting heads or tails is the same. All right, so that's 0.125. Now, what is the probability then that I get 1 or 2 heads? Well, I can get heads, tails, tails, right? I can get tails, head, tails, right? Or I can get tails, tails, heads. Those are 3 possibilities. Well, the possibility of this happening is 0.125, right?
And each one of them is 0.
Add it to 0.125, add it to 0.125.
So it would be 0.37.
So it's 0.375. 2 heads would be the same. I either get heads, heads, tails. I get heads, tails, heads, or I get tails, head, head. So it too is 0.375. So that makes sense? Okay, now we're going to talk about the fundamental counting principle. So if you'll go to the top of page 880, it has gotten dark. Look at the top of page 880.
Oh, good.
Okay, so when we talk about the fundamental counting principle, it's really talking about the value for the total possible outcomes. It's talking about that denominator for the probability. How do we count the total possible outcomes? So it's really, I want you to think, connect that in your brain, that when we're talking about this, we're talking about what would be the denominator, right? And there are really a couple, there's three ways, all right? There's three things. With replacement, okay? So, that is like marbles. That's what's commonly used, all right? Or even dice, okay? With replacement. This is with replacement. All right. Let's say, I was trying to think of an exact example. Let's do rolling dice, okay? With replacement. So now let's do picking marbles. Okay, so let's say I have red 5, green 10, and yellow 15. To make my sample space is this. All right, so if I ask, what is the total possible outcomes of picking a red the first time, putting it back in, and then picking a green? So first time picking a red, second time picking a green. When I replace it, I still have 30 in the bucket, right? So however many times I'm picking, my denominator is always going to be 30, right? And so if you look at the top of the table, this is counting. It must have 26 possible outcomes, and they're picking 3 times. What are the total possible outcomes in the denominator? 17,576. Okay? That's with replacement. Without replacement, there are 2 options. And your book doesn't tie this together very well. And I want to use the numbers 1, 2, and 3. Okay, so we have a permutation, something called permutations, and we have combinations. Permutations is when order is important. The order is extremely important, okay? Order doesn't matter with a combination. Order doesn't matter. With a combination. Okay, so let's look at the numbers 1, 2, and 3. Okay, let's look. How many permutations can we write with those numbers 1, 2, and 3? Well, I could write 1, 2, 3. I could write 1, 3, 2. I actually wrote these down. I want to make sure I get them all.
You could do 2, 3, 1.
Yeah, well, let's do 2, 1, 3, then 2, 3, 1.
3, 1,
3, 1, 2.
2. 3, 2, 1.
3, 2, 1. So there are 6 permutations. 6 possible outcomes. That's my denominator, right? How did we get that? How many choices do we have? 3. 3 times 2 times 1. Or 3 factorial in your calculator. So how many different ways could I arrange a deck of, or let's just say the hearts in a deck of cards? Well, how many cards are there in the deck? How many different permutations could I have?
There are 52 cards.
And so how many hearts in a deck of cards? Come on. 13. Come on. 13. So that there would be 13 factorial total possible permutations. Okay? All right, combinations. It doesn't matter what the order is. There's only one combination. All of these are the same combination. There's only one of them. So if you look in your book, I have 3. I'm choosing 3. I have 3. I'm choosing 3. So this would look like 3 times 2 times 1. That's how many I have over how many I'm choosing. That's just 1. There's only one combination. In the book, they have 26. So maybe they have, if I had, let's say I included 4 and 5 in here. Okay, let's say I included 2 more numbers, all right? If I include 2 more numbers, how many combinations of 3 numbers could I have? How many permutations of 3 numbers chosen from this? Permutations, I could have 5 times 4 times 3. That's how many permutations I could have. Combinations would be 5 times 4 times 3 over 3 times 2 times 1. Because I have 5, that's my numerator, but I'm only choosing 3. So really this would eliminate, that would be 10, that's 10. 10 possible combinations. And then this one would be 20 times 3, 60. There are always more permutations than combinations. Always. Always more permutations than combinations. Okay. I think I want to do, I want to go to 7 because we sort of did 6 and I talked about it. Okay. Suppose you have 4 personalized letters and 4 addressed envelopes. If the letters are randomly placed in the envelopes, what is the probability that all 4 letters will go to the correct address? Okay, does order matter? Order matters because I want the letter written to me, put in my envelope, right? So you're thinking permutations, right? All right, so what is my denominator going to be? I have 4. So 4 times 3 times 2 is what? 4 times 3 times 2 is 24, okay? And there's only one outcome where I get my letter, right? So it's 1 out of 24. You see how they get that? Okay.
Which equals 0.
Right. Okay, well, they went through that big. You can actually do this in your calculator. We'll do it. If I can remember where it is.
Where's one right here?
Okay. All right, so we have 4 letters, 4 envelopes. Because this is the permutation, we're going to choose a permutation, okay? So I got to clear this. So if you're just on your calculating screen, all right, and you input 4, because we have 4 letters, and then if you go to math, at the very top, go to the right to PRB. You see that? That's probability. Go down to number 2. That's NPR is permutation. The one below it is in combination. Okay, so you choose NPR and then 4. And hit enter. What do you get? 24. That's your denominator. Got it? That's not your that's not your probability. That's just your denominator. So when we're talking about how many, this is total possible outcomes when we're looking at combinations and permutations.